4.37 light-years. That's the distance to Alpha Centauri, our closest stellar neighbor. You've probably heard that number before, maybe even nodded along as if it meant something. But here's what nobody tells you. That distance is so incomprehensibly vast, so brutally, terrifyingly large, that if you truly understood it, you'd realize we're not just far from other stars. We're trapped, imprisoned on a tiny rock by distances that mock every achievement humanity has ever made in space exploration. Let me show you what I mean, and I promise, by the end of this, you'll never think about space the same way again. Start with something simple. The moon. We've been there, walked on it, planted flags. It's roughly 240,000 miles away. That trip took Apollo astronauts about 3 days. Not bad, right? Now Mars, our next big target, sits anywhere from 34 to 250 million miles away, depending on where Earth and Mars are in their orbits. At its closest, we're looking at roughly 6 to 9 months of travel time with current technology. These are the distances we talk about when we discuss space exploration. Millions of miles, months of travel. Challenging, sure, but conceivable. Your brain can wrap itself around a 9-month journey. People sail around the world in that time. Some pregnancies last that long. Now let me tell you about Alpha Centauri. "25 trillion miles, not million, not billion, trillion, with a T. That's 25 trillion miles if you want to see all the zeros, or if you prefer metric, about 40 trillion kilometers. The number is so large that writing it out feels almost silly, like trying to count grains of sand on a beach by pointing at each one individually. But raw numbers don't really convey it, do they? Your brain just slides right off them. So let's try this instead. Imagine you could shrink the sun down to the size of a period at the end of a sentence. Just a tiny dot on a page, barely visible. On this scale, where would Alpha Centauri be? Another dot sitting next to it. Across the room, maybe across town. No, it would be 8 miles away. 8 miles of empty space between 2 dots so small you'd need a magnifying glass to see them. You'd have to walk for 2 hours just to get from one period-sized star to another. Here's another way to think about it. If the sun were the size of a grapefruit sitting on a table in Los Angeles, Alpha Centauri would be another grapefruit sitting on a table in New York City. The entire continental United States would fit between our 2 nearest stars if we scaled them down to something you could hold in your hand. These aren't just big distances, they're distances that fundamentally break our intuition about travel, about time, about what's possible. And yet, Alpha Centauri is our nearest neighbor. It's the closest thing we have to a next-door star. Every other star you can see in the night sky is even farther away. Most are hundreds or thousands of light-years distant. Alpha Centauri is the easy trip, the low-hanging fruit, the closest possible destination if we ever want to visit another star system. So what exactly are we dealing with here? Alpha Centauri isn't actually a single star. It's a triple star system, 3 stars bound together by gravity, performing an intricate cosmic dance that's been going on for billions of years. The 2 main stars, Alpha Centauri A and B, orbit each other like binary partners, swinging close enough together to match Saturn's distance from our Sun, then drifting apart to roughly Pluto's orbital distance. This dance takes about 80 years to complete one full cycle. Alpha Centauri A is slightly larger and brighter than our Sun, about 1.1 times its mass. It's a yellow star, the same class as our own, burning steadily in that comfortable middle age that stars like ours enjoy. Alpha Centauri b is a bit smaller and cooler, about 0.9 times the Sun's mass, glowing with an orange hue that speaks to its slightly lower temperature. Then there's Proxima Centauri, the third member of this stellar family, and the actual closest star to our solar system, at 4.24 light-years away. Proxima is the runt of the group, a red dwarf so small and dim you can't see it without a telescope, despite it being our nearest stellar neighbor. It orbits the AB pair at such an enormous distance, about 13,000 astronomical units, that its orbital period is roughly 550,000 years. Think about that. This star takes more than 500,000 years just to complete one orbit around its companions. Proxima is also where things get interesting for anyone dreaming about habitable worlds. In 2016, astronomers discovered Proxima Centauri b, a planet orbiting in the habitable zone of the star. It's roughly Earth-sized, maybe slightly larger, and sits at just the right distance from its star for liquid water to potentially exist on its surface. Before you get too excited though, there's a catch. Actually, several catches. Proxima Centauri is a red dwarf, and red dwarfs are violent stars. They unleash powerful stellar flares that blast their nearby planets with radiation hundreds of times stronger than anything Earth experiences. Proxima b likely gets hit with extreme ultraviolet radiation that could strip away its atmosphere faster than you can say habitable zone. Studies suggest any atmosphere there might be torn away within 10 million years, maybe much faster. The planet might also be tidally locked, meaning one side permanently faces the star while the other side freezes in eternal darkness. Imagine a world where one hemisphere is scorched by an angry red sun, while the other is locked in perpetual night. Not exactly the paradise we're hoping for, but still, it's a planet, in the habitable zone, around the nearest star to our Sun. If we're ever going to visit another star system, this is the one. This is humanity's best shot at reaching another solar system within any reasonable time frame. So how do we get there? Let's start with what we've actually built. The Space Shuttle, that workhorse of orbital missions that flew 135 times between 1981 and 2011, could reach speeds of about 17,500 miles per hour. Impressive for getting into orbit. But if you pointed a space shuttle at Alpha Centauri and somehow kept it flying at that speed indefinitely, the trip would take 148,000 years. Read that again. 148,000 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. A spacecraft traveling at space shuttle speeds, launched when our species first appeared, would still be less than halfway to Alpha Centauri right now. It would arrive around the same time humans developed agriculture for the second time in our history. Maybe the shuttle is too slow. What about our fastest spacecraft? Voyager 1, launched in 1977, is currently the most distant human-made object in existence. It's been flying for nearly 47 years, traveling at about 38,000 miles per hour relative to the Sun. It's now more than 15 billion miles from Earth, far beyond Pluto's orbit, sailing through interstellar space carrying its famous golden record with sounds and images from Earth. And it has covered less than 0.06% of the distance to Alpha Centauri. If Voyager 1 were actually headed toward Alpha Centauri, which it's not, it would take about 75,000 years to get there. That's 75,000 years of continuous travel through the void. 75,000 years ago, humans were still figuring out how to make fire reliably. We were painting on cave walls. We hadn't invented writing, cities, agriculture, or the wheel. The entire span of recorded human history, all of civilization as we know it, covers maybe 5,000 to 6,000 years. Voyager's journey to Alpha Centauri would be 15 times longer than that. The Helios probes, built jointly by NASA and Germany in the 1970s, hold the record for the fastest speed ever achieved by a spacecraft relative to the Sun, reaching about 157,000 miles per hour during their close approaches to our star. Even at that blistering pace, the trip to Alpha Centauri would still take about 18,000 years. These aren't engineering problems we can solve with better rockets or more fuel. Chemical propulsion, the technology that got us to the moon and sent our robots throughout the solar system, simply cannot bridge interstellar distances. The amount of fuel required increases exponentially with speed, and you quickly reach a point where you'd need a fuel tank the size of a planet to accelerate a spacecraft to any meaningful fraction of light speed. It's like trying to cross the Pacific Ocean in a rowboat. Sure, it's theoretically possible. The boat floats, the oars work. But the scale mismatch between your technology and the distance is so enormous that possible becomes meaningless. So what about light itself? Light travels at 186,000 miles per second, or about 671 million miles per hour. At that speed, you could circle Earth's equator 7.5 times in 1 second. You could reach the moon in about 1.3 seconds. Mars, at its closest, in roughly 3 minutes. And Alpha Centauri, 4.37 years. Even at the absolute speed limit of the universe, the fastest anything can possibly travel according to physics, it still takes over 4 years to reach our nearest stellar neighbor. But here's the cruel joke: we can't travel at light speed. The laws of physics forbid it. As objects with mass approach the speed of light, they require exponentially more energy to keep accelerating. To actually reach light speed would require infinite energy, which doesn't exist. Only massless particles like photons can hit that cosmic speed limit. Even if we could somehow reach 10% of light speed, which would require a revolutionary breakthrough in propulsion technology far beyond anything we currently have, the journey would still take 43 years. Launch a mission today, and it might arrive before you die. Maybe, if you're young enough. And if nothing breaks during the 4-decade journey through the radiation-soaked vacuum of interstellar space, 1% of light speed, 437 years. You'd need multiple generations of humans living and dying aboard the spacecraft before it reached its destination. Your great-great-great-great-great-great-great-great-grandchildren might see Alpha Centauri up close. Might, if the ship survives, if the mission continues, if anyone still remembers why they're traveling through the darkness toward a star their ancestors saw only through telescopes. This is what I mean when I say the distances are terrifying. They don't just make space travel difficult, they make it seem impossible in any practical sense. They force us to confront the possibility that interstellar travel might remain forever beyond our reach, that we might be confined to our solar system for the entire duration of human existence. And yet, people are trying, because humans are stubborn, ambitious creatures who refuse to accept that anything is truly impossible. In 2016, a Russian-American billionaire named Yuri Milner stood on a stage in New York City alongside Stephen Hawking and Mark Zuckerberg to announce an audacious plan called Breakthrough Starshot. The goal? Send tiny spacecraft to Alpha Centauri traveling at 20% of light speed, making the journey in just 20 years. 20 years, not 70,000, not 18,000. 20. How? By building something that sounds like science fiction. A ground-based laser array powerful enough to accelerate gram-scale spacecraft equipped with ultra-light sails. Picture something weighing less than a penny, fitted with a sail just meters across, getting blasted by concentrated laser light so intense it would push the craft to relativistic speeds in minutes. The numbers behind this proposal are staggering. The laser array would need to generate 100 gigawatts of power, equivalent to about 100 large nuclear power plants operating simultaneously. It would require coordinating roughly 100 million individual lasers to act as a single coherent beam. The spacecraft would experience acceleration forces of 10,000 times Earth's gravity, forces that would instantly liquefy any human passenger, but which tiny robotic probes might survive. 10 minutes of laser fire, and the craft would be traveling at 20% of light speed. In 20 years, it could reach Proxima Centauri. 4 years after that, assuming everything worked, the first images and data would arrive back on Earth. It sounds like a solution, like maybe we found a way to cheat the terrible distances. But as with everything in space exploration, the devil lives in the details. And those details reveal just how monumentally difficult this actually is. The funding that was supposed to make this happen largely vanished. Remember that $100 million Milner announced alongside Stephen Hawking and Mark Zuckerberg? Researchers who actually worked on Breakthrough Starshot tell a different story. Philip Lubin, a physicist who received Starshot funding, got 2 grants from the initiative, one for $116,000, another for about $80,000. His colleagues in Australia received similar amounts. Over 8 years of work, Lubin's team received less than $200,000 total. That's not even enough to fund a single PhD student's entire doctoral research. Breakthrough contributed less than 5% of the funding in Lubin's program overall. The rest came from NASA and other sources. Lubin calculated that Breakthrough Starshot distributed roughly $4.5 million across about 30 contracts. That's a remarkable gap between the $100 million promised in the glossy press conference and what actually materialized. The public assumed a massive, well-funded initiative was underway. The reality: small teams scraping together modest grants while the world believed humanity was taking its first serious steps toward the stars. But let's assume the funding appears tomorrow. Let's imagine someone writes a check for the full $5 to $10 billion Milner estimated as the real cost. Would that solve our problems? Consider what building this system actually requires. You need approximately 100 million individual lasers working in perfect coordination. Not 100 lasers, not 100,000 lasers, 100 million. Each one must be precisely aimed and timed to combine into a single coherent beam, powerful enough to accelerate a spacecraft to 20% of light speed. These lasers must generate 100 gigawatts of power. To put that in perspective, the world's largest battery can store about 1 gigawatt-hour of energy. You need 100 times that capacity. and you need to discharge it in a controlled manner over about 10 minutes. Building the energy storage alone represents a monumental engineering challenge. Then there's the targeting problem. You're trying to hit a sail meters across with a laser beam while that sail accelerates away from Earth at 10,000 times the force of gravity. The craft will be moving so fast that relativistic effects start becoming relevant. Your beam has to track this accelerating target with perfect precision, maintaining focus over thousands of kilometers as the spacecraft races toward interstellar space. Miss by even a tiny margin and you're just heating empty space while your expensive probe tumbles through the void. Its mission failed before it truly began. But assume you solve all that. Assume you coordinate 100 million lasers, store and discharge 100 gigawatts of power, and hit a meter-wide target traveling at relativistic speeds. Your probe survives the acceleration, deploys its sail properly, and begins the 20-year journey to Alpha Centauri at 1/5 the speed of light. Now it gets interesting. At 20% of light speed, every particle of interstellar dust becomes a bullet. Actually, worse than a bullet. A grain of sand weighing 1 milligram would impact your spacecraft with the kinetic energy of an exploding hand grenade. Your probe weighs less than a penny and has essentially no shielding. The thickness of the sail itself is measured in atoms. The interstellar medium isn't empty. It contains roughly 1 atom per cubic centimeter. That sounds sparse, and by everyday standards it is. But when you're traveling at 60,000 kilometers per second, you're encountering roughly 60,000 atoms every second for every square centimeter of your spacecraft's surface. Most of these will be hydrogen atoms, the lightest element. Even those will gradually erode your probe's surface, bit by microscopic bit, over 20 years of continuous bombardment. But some will be heavier, some will be dust grains, some will be molecules. Any one of them could end your mission instantly. There's no avoiding this. You can't detect and dodge obstacles at these speeds. Light from an obstacle ahead reaches you just microseconds before you slam into it. By the time your sensors register the danger, you've already hit it. The only solution is armor, shielding, some way to protect your delicate electronics and sail from the cosmic sandblasting you'll endure for 2 decades. But you can't add armor. Your entire spacecraft weighs 1 gram. Adding even a microgram of shielding means you need more laser power to accelerate, which means more energy storage, more lasers, more cost. The whole concept depends on making the probe as light as possible. Adding protection undermines the fundamental design. This is the kind of engineering constraint that makes you realize how optimistic the initial proposal was. It's not that the physics is wrong. It's that every solution creates 10 new problems, each as difficult as the last. Let's say your probe somehow survives the journey. 20 years pass. It reaches the Alpha Centauri system, passing Proxima Centauri first because it's slightly closer. You have seconds to gather data before the spacecraft shoots past at 60,000 kilometers per second. At that speed, even Proxima Centauri's gravity won't slow you down meaningfully. You're a bullet passing through a solar system, not a visitor arriving to explore. Your cameras snap photos, your instruments take measurements, your computer processes the data and prepares to transmit. And now you face perhaps the most difficult challenge of all, getting that data back to Earth. Your spacecraft weighs 1 gram. How much power can a gram-scale device generate? Your light sail is your antenna. which means it needs to be shaped to 1 micron precision to function properly. Even if you achieve that engineering miracle, you're trying to transmit a signal across 4.37 light-years with essentially no power behind it. We don't use nanosatellites for interplanetary communication today, precisely because their transmitting power is too weak. Probes like Philae needed to relay data through Rosetta, which then sent it to Earth using much more powerful transmitters. But your Starshot probe has no relay. It's alone, racing past Alpha Centauri, trying to beam data across 25 trillion miles with a transmitter smaller than a postage stamp. The signal would be unimaginably weak by the time it reached Earth. You'd need receiving antennas the size of cities and signal processing sophisticated enough to extract meaning from noise quieter than the cosmic microwave background. Maybe that's possible. Maybe we could build receivers sensitive enough. But it's another massive assumption stacked on top of dozens of others. 4 years after your probe passes Alpha Centauri, that faint signal starts arriving at Earth. If everything worked, if the probe survived the acceleration, if it avoided collisions during the 20-year journey, if its electronics endured 2 decades of cosmic radiation, if the power system still functions, if the antenna deployed correctly, if the signal makes it across the void, if our receivers can detect it, that's a lot of ifs. The people behind Breakthrough Starshot aren't naive. They understand these challenges. The initiative was meant to start research on solutions, to push technology forward, to demonstrate that maybe this isn't completely impossible. But the gap between not completely impossible and actually achievable is wider than most people realize. Here's something most discussions of Breakthrough Starshot skip over. The probe can't slow down. It passes through the Alpha Centauri system at 20% of light speed and keeps going, forever, out into the galaxy, into the space between star systems, until it eventually collides with something or its components degrade beyond function. This isn't really exploration in any meaningful sense. It's a flyby at speeds so extreme you barely have time to glance at your target before it's behind you. Imagine spending $10 billion and 20 years to get a few seconds of observations from Alpha Centauri. It's better than nothing, but it's nowhere close to what people imagine when they think about interstellar missions. What we really want is to slow down, orbit, explore, maybe even land on Proxima Centauri b if it turns out to be interesting. But slowing down requires as much energy as speeding up. You'd need to carry fuel, which means your probe weighs more, which means you need more laser power to accelerate it, which makes everything exponentially harder. Or you'd need to build a second laser array at Alpha Centauri to decelerate the probe when it arrives, which obviously isn't happening. Some proposals suggest using the light sail to brake against the star's radiation when you arrive, but the math doesn't work well. You're moving too fast and the star's light pressure is too weak. You might slow down a bit, but not enough to actually stop. The honest truth? With current physics and even optimistic near-future technology, we can maybe send tiny probes past Alpha Centauri. We probably can't explore it properly. We definitely can't send humans. The distances aren't just large. They're prohibitive in ways that no amount of clever engineering seems likely to overcome. This realization forces a difficult question. If interstellar travel is this hard to our nearest neighbor, what does that say about exploring the galaxy? Because Alpha Centauri isn't special, it's just the closest star. Most stars are much, much farther away. The second closest star system after Alpha Centauri is Barnard's star, almost 6 light-years distant. Then Wolf 359 at 7.9 light-years. Sirius at 8.6 light-years. By the time you reach stars 20 or 30 light-years away, you're looking at centuries-long missions, even at 20% of light speed. The galaxy is 100,000 light-years across. The observable universe contains hundreds of billions of galaxies. The distances that make Alpha Centauri seem almost reachable make the rest of the cosmos completely inaccessible. And this brings us to something nobody wants to talk about, the Fermi paradox. If interstellar travel is this difficult for us, it's equally difficult for anyone else. Every civilization faces the same physics, the same tyranny of the rocket equation, the same energy requirements, the same communication delays. The galaxy is roughly 100,000 light-years across. It contains somewhere between 100 and 400 billion stars. Many of those stars have planets. Some of those planets probably harbor life. Some of that life might be intelligent. Some of that intelligence might be technological. Where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi. If intelligent life is relatively common in the galaxy, and if technological civilizations occasionally arise, and if the galaxy is billions of years old, then statistically, someone should have developed interstellar travel by now. Someone should have spread across the galaxy. Someone should be visible to us. The distances to Alpha Centauri suggest a possible answer. Maybe nobody has colonized the galaxy because nobody can. The distances are too vast. The energy requirements are too extreme. The timescales are too long. This doesn't mean interstellar travel is impossible. It means interstellar colonization might be. You could potentially send probes to nearby stars. You could maybe establish a few outposts over thousands of years. But spreading across the entire galaxy, that might be beyond any civilization, regardless of how advanced they become. Consider what it would take to colonize just our local neighborhood. Within 20 light-years of Earth, there are about 80 star systems. To establish even basic scientific outposts at each one would require technology far beyond anything we currently possess. It would take thousands of years. It would cost more than the entire economic output of human civilization. And that's just 80 stars out of hundreds of billions. The galaxy is incomprehensibly large. The distances between stars aren't just obstacles. They're filters that prevent any civilization from expanding beyond their local stellar neighborhood. But let's zoom back to Alpha Centauri specifically, because even if we can't colonize the galaxy, this one star system represents something important. It's our nearest neighbor, our first potential step beyond the solar system. What makes Alpha Centauri especially interesting is its planetary system. Proxima Centauri has at least 2 confirmed planets, Proxima b and Proxima d. Proxima b was discovered in 2016. It's roughly Earth-sized, orbiting within Proxima Centauri's habitable zone, the region where liquid water could theoretically exist on a planet's surface. This caused enormous excitement. An Earth-sized planet in the habitable zone of our nearest stellar neighbor. It seemed almost too good to be true. It probably is too good to be true. Proxima Centauri is a red dwarf star. These stars are smaller and cooler than our Sun, which means their habitable zones are much closer in. Proxima b orbits its star at just 5% of the distance between Earth and the Sun. It completes one orbit every 11 days. Being that close to a red dwarf creates serious problems. Red dwarfs are extremely active stars. They produce powerful stellar flares that blast nearby planets with radiation. UV radiation, X-rays, charged particles. Research suggests that planets in Proxima Centauri's habitable zone receive radiation exposure hundreds of times greater than Earth. This radiation strips away atmospheres. Models indicate that any Earth-like atmosphere on Proxima b would be lost within about 10 million years, maybe faster. Proxima b is probably tidally locked, meaning one side permanently faces the star, while the other side faces eternal darkness. One hemisphere baked by radiation, the other frozen solid. The only potentially habitable region would be a narrow twilight zone between these extremes. Does this mean Proxima b is definitely uninhabitable? No, but it means the planet faces challenges Earth never encountered. Life there, if it exists, would need to be remarkably resilient. The second planet, Proxima d, is even less promising. It's smaller than Earth, orbiting much closer to the star. It completes an orbit every 5 days. Whatever conditions exist there, they're almost certainly hostile to life as we understand it. So our nearest stellar neighbor has planets, but they're probably not the second Earth we've been hoping for. They're interesting scientifically, worth studying, but probably not habitable. This raises another uncomfortable question about interstellar travel. If we did somehow manage to send humans to Alpha Centauri, where would they go? The planets there don't appear welcoming. You'd need extensive life support systems, underground habitats, radiation shielding. You'd be recreating the challenges of living on Mars, except you're 4 light years from home with no possibility of rescue or resupply. The romantic vision of interstellar travel involves discovering new worlds, walking on alien soil, building new civilizations under foreign stars. The reality is probably more like living permanently in Antarctica, except colder, more dangerous, and infinitely more isolated. But there's another aspect of Alpha Centauri that makes it fascinating beyond just the distance. The system itself is complex, in ways that change how we think about stellar neighborhoods. Alpha Centauri is actually 3 stars. Alpha Centauri A and B orbit each other, coming as close as Saturn's distance from our Sun and swinging out to Pluto's orbital distance. This binary dance repeats every 80 years. Proxima Centauri orbits this binary pair at a distance of about 13,000 astronomical units. That's 430 times farther than Neptune orbits our Sun. The orbit takes 550,000 years to complete. This configuration creates a gravitational environment unlike anything in our solar system. The 2 main stars periodically pass close to each other, potentially disrupting any planets in certain orbital ranges. Proxima's distant orbit means its gravitational influence on the binary pair is minimal, but it's still bound to the system over geological timescales. What would the sky look like from a planet in this system? From Proxima b, Alpha Centauri A and B would appear as 2 bright points of light. Brighter than Venus appears from Earth, but not dramatically so. They'd move slowly across your sky over the course of 550,000 years. From a planet orbiting Alpha Centauri A, you'd see Alpha Centauri b as an intensely bright star, sometimes appearing larger than our moon, sometimes receding to a brilliant point. Proxima wouldn't be visible without a telescope. These gravitational dynamics also affect planet formation. The binary nature of Alpha Centauri A and B might prevent stable planetary orbits in certain regions. Any planets that did form would need to be either very close to one star or very far from both. This complexity is actually typical. Most stars in the galaxy exist in multiple star systems. Our Sun, orbiting alone, is somewhat unusual. If humanity ever does venture to other star systems, we'll need to navigate gravitational environments far more complex than our simple solar system. And there's something else worth considering about Alpha Centauri: its age. Both Alpha Centauri A and B are roughly 5 to 6 billion years old, slightly older than our Sun. Proxima Centauri is harder to age precisely, but it's probably around 4.8 billion years old. This means these stars have been shining for as long as our Sun has existed. Any planets around them have had billions of years to evolve. If life arose on Proxima b, it's had roughly the same amount of time to develop as life on Earth. Of course, this assumes life could survive the radiation environment, the tidal locking, the stellar flares. Those are significant obstacles, but it means that if life did somehow take hold, it's had plenty of time to adapt and potentially become complex. This is why Proxima b remains scientifically compelling despite its challenges. It's not likely to be habitable, but it's not impossible either. And it's close enough that we could potentially study it in detail if we develop the technology. Current telescopes can detect Proxima b's existence and measure some basic properties. Future telescopes might be able to analyze its atmosphere if it has one. We might detect chemical signatures that hint at biological processes. Or we might confirm that the planet is a radiation-blasted rock with no atmosphere at all. But we won't know for certain without going there, or at least sending sophisticated probes. Which brings us back to the fundamental problem: distance. Every question about Alpha Centauri leads back to the same barrier. We want to know more about these planets. We want to study them up close. We want to understand if life could exist there. We want to explore, but we can't. Not with current technology. Probably not with near-future technology. Maybe not ever, depending on how physics actually works at the extreme end of what's theoretically possible. This creates a strange psychological state. We know our nearest stellar neighbor exists. We can see it in the sky. We've detected planets around it. We can calculate exactly how far away it is. We can measure its properties. We can estimate what conditions might be like there. But we can't visit. We can barely even send signals. The star is simultaneously well understood and completely inaccessible. It's like standing on the shore of an ocean, seeing land on the distant horizon, but having no boat. You know the land is there. You can see it clearly on calm days. But the ocean is too wide to swim. The current's too strong. The distance insurmountable. Alpha Centauri sits on humanity's horizon. Close enough to study, too far to reach. A permanent reminder of both how far we've come in understanding the universe and how limited we remain in exploring it. The next nearest star systems don't improve the situation. Barnard's star at 6 light-years, Wolf 3, 5-9 at 8, Sirius at 9. Each additional light-year adds decades or centuries to travel time even at optimistic speeds. The galaxy contains hundreds of billions of stars. The vast majority will never be visited by humans. Many will never be visited by anything we build. The universe is filled with places we can see, but never touch. This isn't meant to be depressing. It's meant to be realistic. The scale of space is not a problem we can engineer around. It's a fundamental feature of the universe we inhabit. But here's what's remarkable. Despite these impossible distances, we keep trying. We keep building better telescopes, developing new propulsion concepts, searching for clever solutions. Maybe someday we'll find a way to make interstellar travel practical. Maybe we'll discover new physics that changes the game. Maybe we'll develop technology that seems impossible today. Or maybe we won't. Maybe Alpha Centauri will remain forever out of reach, a neighbor we can observe but never visit. Either way, understanding the true scale of the distance teaches us something valuable about our place in the cosmos. We live in a universe that's simultaneously intimate and impossibly vast. The universe doesn't care about our curiosity. It doesn't adjust distances to accommodate our ambitions. Alpha Centauri will remain exactly where it is, regardless of how desperately we want to explore it. This might seem obvious, but it's worth stating explicitly because so much science fiction has conditioned us to expect otherwise. We've watched countless movies where characters casually hop between star systems. We've read novels where faster-than-light travel is as routine as catching a bus. We've internalized the idea that distance is just another engineering problem waiting to be solved. It's not. Distance at cosmic scales isn't a technical challenge. It's a fundamental feature of reality. The space between stars isn't empty in the sense of being a void we could fill with better engines or clever solutions. It's vast in a way that resists comparison to anything in human experience. Think about the fastest human-made object ever built. That would be the Parker Solar Probe, which reached speeds around 430,000 miles per hour as it dove toward the Sun. Sounds impressive until you calculate how long that probe would take to reach Alpha Centauri at that speed. About 6,700 years. 6,700 years. That's longer than recorded human history. The Parker Solar Probe could have launched when the first cities were being built in Mesopotamia, and it still wouldn't have arrived yet. And remember, that probe achieved those speeds by falling toward the Sun and using its gravity for acceleration. You can't do that between stars. There's nothing to fall toward in the void. You'd need to generate that speed through propulsion alone, which requires energy. Staggering amounts of energy. How much energy are we talking about? Let's work through some actual numbers. Say you want to accelerate a small spacecraft, just 1 kilogram of mass, to 10% of light speed. That's 30,000 kilometers per second. Fast enough to make the trip to Alpha Centauri in about 43 years instead of millennia. The kinetic energy required for that 1 kilogram spacecraft is roughly equal to the energy released by a nuclear bomb. For 1 kilogram. Scale that up to something that could carry scientific instruments, communications equipment, power systems, and you're talking about energy equivalent to multiple nuclear arsenals. And that's just to accelerate. You also need to decelerate at the destination if you want to actually study anything, rather than just screaming past at relativistic speeds, which means you need double the energy, or you need to carry fuel for deceleration, which adds mass, which requires more energy to accelerate in the first place. This is called the tyranny of the rocket equation. Every bit of fuel you add requires more fuel to push that fuel. The mass grows exponentially. The energy requirements spiral out of control. Chemical rockets, the kind we've used for all human spaceflights so far, simply cannot overcome this barrier. The energy density of chemical fuel is too low. You would need a fuel tank the size of a small planet to accelerate a spacecraft to even a fraction of light speed using conventional rocket propulsion. So what about other propulsion methods? Ion drives, represent a significant improvement. They use electric fields to accelerate ions, generating thrust that's incredibly weak but can operate continuously for years. The Dawn spacecraft used ion propulsion to visit the asteroid belt. It worked beautifully within our solar system. But here's the problem. Even with ion drives operating for thousands of years, you'd only reach a tiny fraction of light speed. The acceleration is just too gentle. You could run an ion drive for 5,000 years and still be looking at multi-generational journeys to reach Alpha Centauri. Nuclear pulse propulsion offers more promise. The concept involves detonating nuclear bombs behind a spacecraft and absorbing the blast with a massive shock absorber plate. It sounds insane, but physicist Freeman Dyson worked out the mathematics in the 1960s as part of Project Orion. The numbers actually work. A spacecraft riding nuclear explosions could theoretically reach 5 to 10% of light speed. That brings Alpha Centauri within reach in a human lifetime. Sort of. The journey would still take 40 to 80 years. Plus, you'd need to carry hundreds or thousands of nuclear devices. Plus the engineering challenges of building a shock absorption system that can survive repeated nuclear detonations. Plus the minor political issue of launching nuclear weapons into space. The project was cancelled for fairly obvious reasons. Fusion propulsion looks more elegant. Instead of exploding nuclear bombs, you'd use controlled fusion reactions, the same process that powers the sun. The exhaust velocity would be much higher than chemical rockets. The fuel is relatively abundant. The concept is theoretically sound, but we still haven't achieved sustained fusion power on Earth. Every fusion reactor built so far consumes more energy than it produces. We've been working on fusion for 70 years. We might be another 70 years from making it practical. And that's just for power generation on Earth, let alone for spacecraft propulsion. Then there's antimatter. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's E equals mc squared. This is the most energy-dense reaction possible under known physics. An antimatter rocket could theoretically reach 50 to 80% of light speed. You could get to Alpha Centauri in 5 to 8 years. The math is beautiful, the engineering is impossible. Why? Because antimatter doesn't exist naturally in any useful quantity. You have to manufacture it. And manufacturing antimatter requires pumping in more energy than you get back out. Current production methods are astoundingly inefficient. Creating 1 gram of antimatter would require more energy than the entire world produces in a year. Even if we solved the production problem, we'd face storage issues. Antimatter annihilates on contact with normal matter. You can't put it in a normal container. You need magnetic containment systems that prevent the antimatter from touching anything physical. These systems require power, lots of power, continuously. If the power fails for even a fraction of a second, your entire fuel supply detonates. Every propulsion system we can imagine runs into walls. Fundamental walls, not just technical hurdles. Which brings us to the most ambitious proposal yet attempted, Breakthrough Starshot. Announced in 2016 by billionaire Yuri Milner, alongside Stephen Hawking, the concept seemed radical but achievable. Instead of carrying fuel, you'd use light sails, thin reflective sheets pushed by laser beams from Earth. The spacecraft itself would be tiny, gram-scale, a chip with miniaturized sensors and electronics attached to a sail just meters across. The lasers would be enormous, a phased array of 100 million individual laser units combining their beams to deliver 100 gigawatts of power. That's 100 gigawatts, equivalent to about 100 large nuclear power plants operating simultaneously, focused into a beam narrow enough to push a sail at interstellar distances. The acceleration would be brutal, 10,000 times Earth's gravity for about 10 minutes. But the spacecraft has no passengers to crush, just electronics designed to survive the forces. After 10 minutes of acceleration, the craft would be moving at 20% of light speed, fast enough to reach Alpha Centauri in about 20 years. The project had $100 million in funding. Major institutions were involved. Smart people thought it could work. 7 years later, the reality looks different. The $100 million never fully materialized. Most researchers involved received tiny grants, $80,000 here, $100,000 there. Total spending appears to have been around $4.5 million across 30 contracts. That's not nothing, but it's nowhere near what would be needed to actually build the system. And the technical challenges are staggering. You need 100 million lasers working in perfect synchronization. One laser out of alignment and the beam disperses. The sail misses the push. The mission fails. You need to focus that beam accurately across thousands of kilometers as the spacecraft accelerates away. The targeting requirements are absurd. You're trying to hit a target the size of a dinner table that's moving at an appreciable fraction of light speed. You need to prevent the sail from vaporizing under the intense laser light. The power density is enormous. The sail needs to be reflective enough to bounce most of the light back, but any absorption at all creates heat. Too much heat, and the sail burns up before reaching speed. You need the spacecraft to survive the journey through interstellar space. At 20% of light speed, hitting a grain of dust releases energy equivalent to an exploding hand grenade. The interstellar medium isn't completely empty. There's gas and dust out there. Even at incredibly low densities, impacts at these velocities are catastrophic. You need the spacecraft to send data back to Earth. This might be the hardest part. The entire spacecraft weighs grams. It has minimal power available. The signal needs to travel 4.37 light-years back to Earth. By the time it arrives, that signal will be incredibly weak. Jim Benford, an expert in the field, pointed out that the sail itself would need to serve as the antenna. It would need to be shaped to 1-micron precision to function properly. And even then, generating enough power to transmit across interstellar distances from a gram-scale spacecraft seems nearly impossible. For comparison, current interplanetary probes like those visiting Mars or Jupiter need large dish antennas and significant power systems just to transmit back to Earth. Philae, the probe that landed on a comet, needed to relay its data through the larger Rosetta spacecraft, which then sent signals to Earth. Breakthrough Starshot has no such relay system. The tiny craft is entirely alone. These aren't problems that get solved by trying harder or being smarter. They're fundamental constraints imposed by physics and engineering reality. Maybe future breakthroughs will change the equation. Maybe someone will discover new physics that allows faster-than-light travel. Maybe we'll develop technologies we can't currently imagine. But betting on unknown future breakthroughs is hoping, not planning. And hope doesn't move spacecraft across interstellar distances. What we're left with is a strange situation. We can see Alpha Centauri clearly. We can measure its properties. We've detected planets there. We know exactly where it is and approximately what conditions are like in that star system. But we cannot visit, not with current technology, probably not with near-future technology, possibly not ever, depending on whether the universe allows loopholes in the laws of physics. The distance isn't just inconvenient, it's prohibitive in a fundamental sense. Alpha Centauri might as well be in another dimension for all the practical access we have to it. This creates an interesting psychological state. We're scientifically advanced enough to detect and study distant star systems, but we're not advanced enough and might never be advanced enough to actually explore them physically. We can observe, we cannot touch. Every telescope we build, every detection method we develop, every analysis technique we perfect only reinforces this barrier. We learn more about places we cannot reach. We find more planets we cannot visit. We identify more potentially habitable worlds that will forever remain beyond our grasp. The universe reveals itself to our instruments while remaining closed to our presence. It's simultaneously knowable and inaccessible. A cosmic museum where we can see the exhibits but never enter the rooms. Some people find this depressing. The vastness of space means most of the universe will never be explored by humans or anything humans build. The galaxy contains hundreds of billions of stars. We might visit a few dozen in our solar neighborhood if we're extraordinarily lucky and persistent. The rest remain forever out of reach. But there's another way to look at it. The scale of the universe guarantees there will always be mysteries, always be frontiers, always be questions we cannot answer through direct investigation. Alpha Centauri sits on our horizon, close enough to study, but too far to reach. It's a permanent reminder of both our capabilities and our limitations. We've come far enough to see it clearly. We remain too limited to visit, and that distance creates something else worth considering. Every scientific fact we know about Alpha Centauri comes from light. Photons that left those stars years ago and traveled across the void to reach our telescopes. We've never touched Alpha Centauri, never sampled its stellar wind, never measured its magnetic field up close. Every measurement is indirect, every observation filtered through distance and atmosphere and instrumental limitations. What we think we know might be incomplete or subtly wrong. The planets we've detected around Proxima Centauri, Proxima b, and Proxima d were found through the radial velocity method. We watch the star wobble slightly as orbiting planets pull on it gravitationally. From that wobble, we calculate mass, orbital period, distance from the star. It's detective work. Impressive detective work that's revealed thousands of exoplanets across the galaxy. But it's not the same as being there. Proxima b orbits its star every 11.2 days. It sits in the habitable zone, that region where liquid water could theoretically exist on a planet's surface. This makes it interesting, potentially very interesting. But the habitable zone around a red dwarf star like Proxima Centauri is nothing like Earth's comfortable orbit around our yellow sun. Red dwarfs are violent. They produce massive stellar flares that blast nearby planets with radiation. Proxima Centauri is no exception. Studies suggest that Proxima b receives ultraviolet radiation hundreds of times more intense than Earth experiences. That radiation strips atmospheres. It tears apart water molecules. It makes the surface environment brutally hostile to anything resembling terrestrial life. The models show Proxima Centauri's radiation could strip an Earth-like atmosphere at rates 10,000 times faster than what happens here. Some researchers concluded that any atmosphere on Proxima b would be lost within 10 million years. That sounds like a long time. But 10 million years is nothing in cosmic terms. A planetary blink. There's another problem. Proxima b is probably tidally locked, one face permanently pointing toward its star, the other forever in darkness, the day side baked by stellar radiation, the night side frozen. Temperature extremes that would create hellish conditions unless something else is happening. Strong atmospheric winds, perhaps, redistributing heat around the planet. But we don't know if Proxima b has an atmosphere at all. This is what makes the distance so frustrating. We can detect the planet. We can estimate its mass and orbit. We can model what conditions might be like on its surface. But we cannot confirm any of it directly. The planet remains a collection of educated guesses based on incomplete data transmitted across 4.24 light-years of empty space. Proxima d, the other confirmed planet, orbits even closer. Just 3% of the Earth-Sun distance. It completes an orbit every 5 days. With about a quarter of Earth's mass, it's one of the lightest exoplanets ever detected. Also almost certainly uninhabitable. Too close to its violent star. Too small to hold onto an atmosphere against the stellar wind. Both planets are fascinating from a scientific perspective. They're real worlds orbiting our nearest stellar neighbor, but they're not the Earth-like paradise some people imagine when they think about traveling to Alpha Centauri. They're harsh, radiation-blasted rocks circling an angry red star, and we cannot visit them to learn more. The gap between detection and exploration is massive. We've gotten very good at finding planets around other stars. Thousands have been catalogued, some in habitable zones, some roughly Earth-sized, some that might have liquid water on their surfaces. But finding them and reaching them are completely different challenges. It's like having incredibly powerful binoculars that let you see individual houses in a city on the opposite side of the world. You can count the windows, estimate the building materials, watch lights turn on and off, but you cannot walk through the front door, cannot explore the interior, cannot meet anyone who lives there. The binoculars are amazing. The distance remains insurmountable. This creates a strange situation for astronomy. The field has advanced to the point where we can characterize exoplanet atmospheres by analyzing starlight filtered through them during transits. We can detect potential biosignatures, chemical compounds that might indicate life. We can build increasingly detailed models of distant planetary systems, but we're permanently limited to remote observation. Physical exploration requires technology we don't have and might never develop. Some people argue this is fine. We don't need to visit Alpha Centauri. Remote observation tells us what we need to know. Build better telescopes. Develop more sensitive detection methods. Launch space-based observatories that can study exoplanets without atmospheric interference. This approach has yielded tremendous results. It will continue yielding results. But it cannot replace actually being there. Consider what we've learned from the planets in our own solar system. Mars rovers have discovered things that telescopes never could. The specific chemistry of Martian soil, the way wind shapes sand dunes, the presence of organic molecules in ancient lake beds. Cassini at Saturn revealed details about the moon Enceladus, an underground ocean, geysers of water ice, potential chemical energy for life that would have been impossible to detect from Earth. Being there makes all the difference. We'll never have that for Alpha Centauri, the rovers trundling across Proxima B's surface, the orbiter mapping its terrain, the atmospheric probe measuring composition and temperature at different altitudes. These remain science fiction, not because we lack imagination, because we lack propulsion. The psychological impact of this limitation is interesting. Previous generations of humans always had frontiers they could theoretically reach. Distant lands across oceans, unexplored continents, eventually space itself. The moon was far away. Getting there was difficult, but it was possible. We did it. Alpha Centauri is different. It's not just difficult, it's likely impossible with any technology that respects known physics. We've hit a wall, an absolute barrier imposed by the structure of space-time itself. The speed of light isn't a challenge to overcome through better engineering. It's a fundamental limit to how quickly information and matter can move through the universe. This means humanity might be permanently confined to our local stellar neighborhood. Maybe we'll eventually build generation ships, massive vessels that take thousands of years to reach nearby stars, with the descendants of the original crew arriving at the destination. Maybe we'll develop hibernation technology that lets humans sleep through centuries-long journeys. Maybe some breakthrough we cannot currently imagine will change the equation, but more likely, we're stuck. Alpha Centauri remains visible, remains measurable, remains forever out of reach. There's something almost cruel about this arrangement. The universe shows us wonders through our telescopes, thousands of exoplanets, billions of galaxies. Structure and complexity beyond anything our ancestors imagined. But it places these wonders behind an impenetrable barrier of distance. We can see, we cannot touch. It's the ultimate window shopping experience. Everything on display, nothing available for purchase. The nearest star system sits 25 trillion miles away. We can measure that distance precisely. We cannot cross it practically. The numbers are clear. The physics is unambiguous. The conclusion is unavoidable. Alpha Centauri might as well be in another universe for all the access we have to it. This doesn't stop us from trying. Research continues into advanced propulsion concepts, laser-pushed light sails, nuclear pulse drives, antimatter rockets, fusion ramjets that scoop up interstellar hydrogen for fuel. Each concept faces enormous technical challenges. Each would require decades or centuries of development. Each might ultimately prove impossible to build at the scale required. But humans keep trying because the alternative is accepting permanent limits. Acknowledging that some destinations will never be reached. Admitting that the universe is bigger than our ability to explore it. These are difficult truths for a species that's grown accustomed to pushing boundaries. The distance to Alpha Centauri teaches humility, not through cruelty or punishment, just through existence. It sits there close enough to see clearly, far enough to remain untouchable. A permanent reminder that the cosmos operates on scales that dwarf human capabilities. Every photon that reaches us from those stars traveled for years across empty space. They carry information encoded in their wavelengths, but they cannot carry us back along their path. The journey works in only one direction. Light reaches Earth. Nothing from Earth reaches Alpha Centauri except radio signals that will take years to arrive and accomplish nothing except marking our presence in the cosmic void. We exist in a universe we can observe but barely explore. Our instruments peer deep into space and time. Our spacecraft venture to the edge of the solar system, but the stars remain distant. The galaxy remains vast. The distances remain terrifying. Alpha Centauri waits on the horizon, close and impossibly far simultaneously. It's there every night in the southern sky. You can point to it. You can measure its properties. You can detect its planets. You cannot visit. That permanence forces a question nobody wants to confront directly. What if this is it, not temporarily, not until better technology arrives, just permanently? What if humanity's descendants in the year 5,000 or 10,000 face exactly the same barriers we face today? Same physics, same distances, same impossibilities. The optimistic narrative assumes progress. Better rockets, smarter engineering, breakthrough discoveries that render current limitations obsolete. History supports this assumption. Problems that seemed insurmountable eventually yielded to human ingenuity. But interstellar distances don't care about ingenuity. They exist independent of human capability. The gap between here and Alpha Centauri won't shrink because we got clever. The speed of light won't increase because we need it to. The energy requirements won't decrease because we developed better batteries. Physics sets hard limits. Some problems don't have solutions, only workarounds that remain prohibitively expensive forever. Consider the energy equation again. Accelerating a single gram to 20% of light speed requires energy equivalent to several kilotons of TNT. That's not an engineering challenge. That's a fundamental relationship between mass, velocity, and kinetic energy. You can't engineer your way around E equals 1/2 mv squared. The equation doesn't care about your propulsion system or your fuel source. It simply describes how much energy any object requires to reach any velocity. Scaling up from grams to tons multiplies the problem by millions. A modest spacecraft weighing just 1 ton would require energy equivalent to billions of tons of TNT to reach 20% light speed. That's comparable to the entire nuclear arsenal of every nation on Earth. And that's just acceleration. You also need identical energy for deceleration, unless you plan to zip through the Alpha Centauri system at relativistic speeds without stopping. Double the energy requirement. Then add shielding against interstellar radiation and micrometeorite impacts. Add life support systems if humans are aboard. Add computing systems, communication equipment, scientific instruments. Add redundancy because nothing can be repaired during a decades-long journey through absolute void. The mass grows. The energy requirement grows with it. The problem compounds. Some proposals suggest building the infrastructure in space to avoid lifting mass from Earth's gravity well. Reasonable idea, but you still need to construct that infrastructure, still need to transport materials, still need to generate and store stupendous amounts of energy. The breakthrough Starshot concept recognizes these limitations. Their solution: make the spacecraft absurdly small. Gram-scale probes propelled by ground-based lasers, no onboard propulsion, no fuel to carry, just a tiny chip with a reflective sail catching laser light. Even this minimal approach faces staggering challenges. The laser array needs to generate 100 gigawatts of power. That's roughly equivalent to 100 large nuclear reactors firing simultaneously. The entire array must focus coherently on a sail measuring just meters across. This targeting precision must be maintained as the spacecraft accelerates away at thousands of kilometers per second. The sail must survive temperatures that would vaporize most materials. The gram-scale payload must include functional cameras, computers, communication systems, and power generation. Oh, and it needs to transmit data back across 4 light-years of space using a power source smaller than a coin. The technical obstacles here aren't just difficult. Some might be fundamentally insurmountable. How do you communicate across interstellar distances when your entire power budget barely exceeds a watch battery? How do you protect gram-scale electronics from decades of cosmic radiation exposure? How do you ensure the sail maintains structural integrity through acceleration forces exceeding 10,000 times Earth's gravity? Nobody knows. The answers might not exist. And Breakthrough Starshot represents the absolute minimum viable approach. Tiny probes, no humans. One-way journey, no possibility of return, no in-system maneuvering, just a flyby lasting hours as the probe screams through at relativistic speeds. Even this proves extraordinarily difficult. Scaling up to crewed missions multiplies every problem by factors of millions or billions. The energy requirements become comparable to entire civilizations' power output. The journey duration extends to generations. The costs exceed anything humanity has attempted. Some theorists propose world ships, massive vessels containing complete ecosystems, rotating habitats generating artificial gravity, populations numbering thousands living and dying during centuries-long transits. These concepts appear regularly in science fiction for good reason. They represent one of the few, somewhat plausible approaches to interstellar travel. But somewhat plausible still means virtually impossible. The engineering challenges of constructing a kilometers-long spacecraft in orbit dwarf anything humanity has built. The social challenges of maintaining a stable society for multiple generations in complete isolation would be unprecedented. The economic challenges of funding such a project would require global cooperation on a scale never achieved. And at the end of decades or centuries of effort, you've transported a few thousand people to another star system where they face unknown conditions on potentially uninhabitable worlds. Maybe worth it, maybe not. Depends entirely on what you're fleeing or seeking, but definitely not happening with anything resembling current or near-future technology. The alternatives get progressively more speculative. Suspended animation that lets humans sleep through the journey requires biology we don't possess. Uploading human consciousness to digital substrates requires neuroscience we don't possess. Wormholes or warp drives that circumvent normal space require physics we don't possess. Each solution demands breakthroughs in fundamental science, not incremental improvements. Revolutionary discoveries that overturn current understanding. Possible. Maybe. Probable. No. Most of physics has been thoroughly tested. Relativity has passed every experimental challenge for over a century. Quantum mechanics accurately predicts phenomena across dozens of orders of magnitude. The Standard Model describes particle interactions with absurd precision. These theories might be incomplete. They're certainly not wrong within their tested domains. Any new physics must reduce to known physics in all the regimes we've already explored. That constrains possibilities dramatically. You can't just propose arbitrary new physics that would make interstellar travel easy. It has to remain consistent with everything we've already measured. Those measurements include the behavior of matter and energy at extreme velocities, high energies, and large scales. The room for revolutionary surprises keeps shrinking as experimental precision improves. Which brings us back to the uncomfortable question: what if the universe simply doesn't allow easy interstellar travel? What if the enormous distances between stars represent a fundamental isolation mechanism? What if intelligent civilizations arise, develop technology, peer into the cosmos, and discover they're trapped in their home systems by physics itself? This could explain the Fermi paradox. Where is everybody? If the galaxy teems with life, why haven't we detected it? Maybe because interstellar travel is impossible for everyone. Maybe every civilization hits the same wall. Maybe they all develop radio telescopes and detect hints of other worlds. Maybe they all calculate the distances and energy requirements. Maybe they all reach the same depressing conclusion. We're alone, not because life is rare, because distance is vast. Each civilization exists in its own isolated bubble, able to observe, unable to visit. The galaxy might contain millions of technological species, all trapped in their respective solar systems, all staring at the same unreachable stars. It's a lonely thought, but it fits the evidence better than most alternatives. We see no alien visitors because they face the same barriers we face. We detect no alien signals because interstellar communication faces similar challenges to interstellar travel. The energy required to transmit detectable signals across light years is enormous. The chances of aiming that transmission correctly toward another civilization are infinitesimal. The universe might be full of life. Just very, very quiet life. Each species isolated by distance and physics. Alpha Centauri exemplifies this isolation perfectly. It's right there. Closest possible target. We can see it clearly. We know its composition, its motion, its planets. We cannot reach it. If we can't reach our nearest neighbor, what hope exists for more distant systems? What chance of ever exploring the galaxy? What possibility of encountering other civilizations? The romantic vision of humanity spreading among the stars might be exactly that. Romance, fiction, fantasy. Reality might be staying home, building telescopes instead of starships, observing instead of exploring, learning to accept that some things remain forever beyond reach, regardless of desire or determination. That's not how humans usually respond to challenges. We're a species that climbed mountains because they were there, that crossed oceans in wooden boats, that walked on the moon because it seemed impossible. But eventually, every civilization encounters limits, things that truly cannot be done regardless of effort or ingenuity. Alpha Centauri might represent that limit for us. The unreachable destination that teaches humility through sheer existence. We'll keep trying, keep designing, keep calculating, keep hoping for breakthroughs. But Alpha Centauri will keep sitting there, 25 trillion miles away, neither knowing nor caring about human ambition. It will continue its slow orbit around the galactic center. Its stars will continue fusing hydrogen into helium. Its planets will continue their endless circuits, and Earth will continue its own orbit around a different star, separated from its nearest stellar neighbors by distances that might as well be infinite for all our ability to cross them. We can measure those distances precisely. We cannot traverse them practically. That knowledge becomes its own kind of achievement. Knowing the distance, understanding the barrier, calculating exactly what would be required to cross it. Previous generations imagined space travel through pure fantasy. Rockets to the moon, drawn by Jules Verne. Martian Canals conceived by Percival Lowell, fiction unbounded by reality. We've moved beyond fantasy into something harder. We know the actual numbers. We understand the real physics. We see the gap between current capability and required capability with painful clarity. That clarity doesn't make the distance smaller. It makes it more real. Consider what Alpha Centauri represents in human terms. Not astronomical units or light years, human terms. Alpha Centauri is every dream deferred by reality, every ambition limited by physics, every hope confronted by mathematics. It's the destination that should be reachable but isn't. The neighbor that should be accessible but remains isolated. The goal that appears achievable until you calculate what achievement requires. Engineers understand this frustration intimately. You can design perfect systems on paper. You can solve theoretical problems elegantly. Then material science limits what you can build. Thermodynamics restricts what you can achieve. Physics says no. Alpha Centauri is physics saying no at cosmic scale. But humans are remarkably persistent creatures. We don't accept no easily. We find workarounds. We develop new technologies. We solve problems that seemed impossible. Moon landings seemed impossible until they weren't. Heavier than air flight seemed impossible until it wasn't. Splitting atoms seemed impossible until it wasn't. Maybe Alpha Centauri follows the same pattern. Maybe today's impossible becomes tomorrow's merely difficult. That optimism crashes against specific numbers. Voyager 1 travels at 17 kilometers per second. Sounds fast. That's over 60,000 kilometers per hour. That's escaping the entire solar system. Yet Voyager 1 has covered less than 0.06% of the distance to Alpha Centauri after nearly 50 years of continuous travel. Extrapolate that progress. Voyager reaches Alpha Centauri in roughly 70,000 years. That's not an engineering problem. That's a civilizational timescale problem. Even dramatically improved propulsion doesn't change the fundamental equation much. Suppose we build spacecraft 10 times faster than Voyager. That's 170 kilometers per second. Impressive by current standards. Still requires 7,000 years to reach Alpha Centauri. 100 times faster gets you down to 700 years. Still multiple human lifetimes. Still longer than most nations have existed. Still longer than most languages survive unchanged. The Breakthrough Starshot project aimed for 20% light speed. That's genuinely revolutionary. That gets travel time down to about 20 years for the journey. Add 4 years for the signal to return. You launch a probe and might see results within your own lifetime. That's transformative. That changes everything. That makes interstellar exploration conceivable rather than purely theoretical. Except Breakthrough Starshot faces obstacles that might prove insurmountable. The energy requirements alone stagger comprehension. Accelerating even a gram-scale spacecraft to 20% light speed requires energy equivalent to several kilotons of TNT. The laser array needs to generate 100 gigawatts of power. That's roughly 100 large nuclear power plants firing simultaneously. For 10 minutes, to launch one tiny probe. Then you need to repeat that process for every additional probe. The infrastructure costs would exceed most nations' space budgets for decades. Then there's the coordination problem. The proposal requires approximately 100 million lasers acting as a single coherent beam, focusing on a sail just meters across, maintaining that focus as the spacecraft accelerates away at tremendous speed. Any misalignment destroys the probe. Any fluctuation in power burns through the sail. The precision required exceeds anything humanity has built at comparable scale. Even if you solve those problems, you face the interstellar medium. Space isn't empty. It contains dust particles, hydrogen atoms, tiny grains of matter. At 20% light speed, colliding with a dust grain releases energy equivalent to an exploding hand grenade. A spacecraft traveling at those velocities needs shielding that can survive continuous impacts. But shielding adds mass. Added mass requires more energy to accelerate. More energy means bigger lasers and more infrastructure. The requirements spiral upward. Assume you solve everything. You launch a successful probe. It reaches Alpha Centauri 20 years later. It begins transmitting data. Now you face the communication challenge. The probe weighs grams. It has minimal power for transmission. Its signal spreads across 4 light-years of distance. By the time that signal reaches Earth, it's almost indistinguishable from background noise. You need enormous receiving arrays, sophisticated signal processing, years of observation time to extract meaningful data from the faint whisper crossing interstellar space. Every technical challenge has theoretical solutions: better materials, more powerful lasers, improved electronics, clever engineering. But theoretical solutions require practical implementation. They require funding, political will, sustained effort across decades, international cooperation. None of those things are guaranteed. Most ambitious space projects fail not from technical inadequacy, but from withdrawn funding or lost political support. The International Space Station represents humanity's most expensive single object ever built. Roughly $150 billion invested over decades. Multiple nations contributing. It orbits 400 kilometers above Earth. Alpha Centauri sits 40 trillion kilometers away. That's a factor of 100 billion times farther. Even accounting for technological progress and economies of scale, the cost differential remains staggering. Maybe that's acceptable. Maybe humanity should invest enormous resources in reaching Alpha Centauri, even if success remains uncertain. Maybe the attempt itself justifies the cost. Maybe pushing against impossible limits advances science and technology in unexpected ways. Apollo didn't just land people on the moon. It drove innovation in materials science, computer technology, systems engineering. Maybe an Alpha Centauri mission would do the same at larger scale. Or maybe that investment would be better spent elsewhere. Better telescopes to observe Alpha Centauri from Earth. Better instruments to detect its planet's atmospheres. Better models to simulate potential habitability. You can learn enormous amounts about distant star systems without sending physical probes. The James Webb Space Telescope revealed unprecedented detail about exoplanet atmospheres from Earth orbit. Future telescopes will see more. Direct observation might provide better science per dollar than interstellar missions. This creates philosophical tension. Do we explore because exploration yields practical benefits? Or because exploration represents something fundamental about human nature? Are we trying to solve scientific problems or satisfy psychological needs? The answer determines how we approach Alpha Centauri. If it's about science, stay home and build bigger telescopes. If it's about human identity and destiny, launch the probes regardless of cost. Both perspectives have merit. Both reflect genuine human values, but they suggest different futures. One future finds humanity building increasingly sophisticated instruments to observe the cosmos from our solar system, becoming expert astronomers, masters of remote sensing, understanding the universe through careful observation from a distance. The other future sees humanity struggling to build interstellar probes, launching tiny craft into the void, waiting decades for responses, gradually extending our physical presence beyond the solar system, even if that process takes centuries or millennia. Neither future is wrong. Neither is right. They're just different paths forward, different responses to the same basic reality that Alpha Centauri sits very far away. That distance doesn't care about human preferences. It doesn't accommodate our desires. It simply exists. Physics doesn't negotiate. Some might find that depressing. The universe's indifference to human ambition, the cold mathematics of distance and energy, the barriers that technology can't easily overcome. But there's also something clarifying about hard limits. They force honesty. They prevent wishful thinking. They make you confront reality as it actually exists rather than as you wish it existed. Alpha Centauri teaches humility through sheer existence, not the false humility of pretending humans are insignificant. We're not. We're remarkable. We built civilization. We developed science. We explored our own planet thoroughly and began exploring nearby space. That's genuinely impressive for a species that only developed agriculture 10,000 years ago. But impressive doesn't mean unlimited. Capability doesn't mean omnipotence. We can do extraordinary things within our domain. We struggle beyond it. That limitation might be universal. Other civilizations around other stars probably face similar constraints. They probably developed radio telescopes and detected hints of planets orbiting distant suns. They probably calculated the distances and energy requirements. They probably reached similar conclusions about the practical impossibility of casual interstellar travel. They're probably trapped in their home systems just as we're trapped in ours. All of us able to observe, unable to visit. The galaxy might contain thousands of intelligent species, all isolated by distance, all staring at unreachable neighbors. If that's true, it changes how we should think about the search for extraterrestrial intelligence. We're not looking for visiting aliens. We're looking for radio signals from distant civilizations who face the same isolation we face, who developed similar technology, who made similar discoveries, who reached similar limitations. The search becomes about finding others in the same situation rather than expecting visitors who somehow overcame barriers we can't overcome. Maybe that's the real lesson of Alpha Centauri. Not that humans are insignificant, that the universe is big, profoundly big, big enough that distance itself becomes an isolating factor, big enough that proximity is relative, big enough that nearest neighbor still means impossibly far. We live in a universe where you can see other destinations clearly but cannot reach them practically, where knowledge exceeds capability, where understanding outpaces action. That's not a comfortable realization. Humans prefer problems they can solve through effort and ingenuity. We like challenges that yield to persistence. Alpha Centauri doesn't yield. It sits there, visible, known, characterized, unreachable. A permanent reminder of limitation. Not a temporary obstacle awaiting the right technology. A fundamental barrier built into the architecture of space and time. You can measure the distance precisely. You can calculate trajectories accurately. You can design theoretical missions completely. You cannot travel there within relevant human timescales using known physics. That's not pessimism. That's accuracy. The math doesn't lie. The physics doesn't care. Alpha Centauri remains exactly where it is, regardless of human wishes. Future generations might develop technologies we can't currently imagine, physics we don't yet understand, methods that bypass current limitations. That's possible. History shows technology advancing in unexpected directions, but betting on unknown future breakthroughs means admitting current approaches are inadequate. It means accepting we can't reach Alpha Centauri now. Maybe not for centuries. Maybe not ever. Some will continue trying anyway. Some will dedicate careers to developing better propulsion, to solving the energy problems, to designing workable interstellar probes. That work has value even if it never succeeds. Even if Alpha Centauri remains forever beyond reach. The attempt teaches us about engineering limits, physical constraints, the nature of space itself. Others will focus on observation rather than travel, on understanding Alpha Centauri from a distance, on characterizing its planets remotely, on determining whether life exists there without ever visiting. That approach also has value, also advances knowledge, also satisfies curiosity about our nearest stellar neighbor. Both approaches accept the same underlying reality. Alpha Centauri is far, terrifyingly far, so far that human intuition fails to grasp the distance, so far that conventional travel becomes meaningless, so far that even revolutionary propulsion barely makes a dent in journey time. The distance doesn't shrink because we want it to. It remains fixed, absolute, uncaring. That's what makes it terrifying. Not that it's dangerous, that it's indifferent. The universe doesn't notice human ambition, doesn't accommodate our dreams, doesn't care whether we explore or stay home. Alpha Centauri will continue orbiting the galaxy whether we visit or not. Its planets will continue their endless circuits regardless of human interest. The stars will burn, the distances will remain, and Earth will keep circling its own star, separated from its nearest neighbors by gulfs that might as well be infinite. Human access provided the script_1 and script_2 as examples, along with detailed formatting guidelines and instructions to create Part 7, final part, of a script about Alpha Centauri's terrifying distance. The output should be exactly 2,285 words. Maintain perfect continuity with Part 6's ending, and follow the AVD optimization guidelines. The script should end conclusively without a traditional outro. We can measure those distances precisely. We cannot traverse them practically. That knowledge becomes its own kind of achievement. Knowing the distance, understanding the barrier, calculating exactly what would be required to cross it. Previous generations imagined space travel through pure fantasy. Rockets to the moon drawn by Jules Verne, Martian canals conceived by Percival Lowell, fiction unbounded by reality. We've moved beyond fantasy into something harder. We know the actual numbers. We understand the real physics. We see the gap between current capability and required capability with painful clarity. That clarity doesn't make the distance smaller. It makes it more real. Consider what Alpha Centauri represents in human terms. Not astronomical units or light years. Human terms. Alpha Centauri is every dream deferred by reality, every ambition limited by physics, every hope confronted by mathematics. It's the destination that should be reachable but isn't. The neighbor that should be accessible but remains isolated. The goal that appears achievable until you calculate what achievement requires. Engineers understand this frustration intimately. You can design perfect systems on paper. You can solve theoretical problems elegantly. Then material science limits what you can build. Thermodynamics restricts what you can achieve. Physics says no. Alpha Centauri is physics saying no at cosmic scale. But humans are remarkably persistent creatures. We don't accept no easily. We find workarounds. We develop new technologies. We solve problems that seemed impossible. Moon landings seemed impossible until they weren't. Heavier than air flight seemed impossible until it wasn't. Splitting atoms seemed impossible until it wasn't. Maybe Alpha Centauri follows the same pattern. Maybe today's impossible becomes tomorrow's merely difficult. That optimism crashes against specific numbers. Voyager 1 travels at 17 kilometers per second. Sounds fast. That's over 60,000 kilometers per hour. That's escaping the entire solar system. Yet Voyager 1 has covered less than 0.06% of the distance to Alpha Centauri after nearly 50 years of continuous travel. Extrapolate that progress. Voyager reaches Alpha Centauri in roughly 70,000 years. That's not an engineering problem. That's a civilizational timescale problem. Even dramatically improved propulsion doesn't change the fundamental equation much. Suppose we build spacecraft 10 times faster than Voyager. That's 170 kilometers per second. Impressive by current standards. Still requires 7,000 years to reach Alpha Centauri. 100 times faster gets you down to 700 years. Still multiple human lifetimes. Still longer than most nations have existed. Still longer than most languages survive unchanged. The Breakthrough Starshot project aimed for 20% light speed. That's genuinely revolutionary. That gets travel time down to about 20 years for the journey. Add 4 years for the signal to return. You launch a probe and might see results within your own lifetime. That's transformative. That changes everything. That makes interstellar exploration conceivable rather than purely theoretical. Except Breakthrough Starshot faces obstacles that might prove insurmountable. The energy requirements alone stagger comprehension. Accelerating even a gram-scale spacecraft to 20% light speed requires energy equivalent to several kilotons of TNT. The laser array needs to generate 100 gigawatts of power. That's roughly 100 large nuclear power plants firing simultaneously. For 10 minutes, to launch one tiny probe. Then you need to repeat that process for every additional probe. The infrastructure costs would exceed most nations' space budgets for decades. Then there's the coordination problem. The proposal requires approximately 100 million lasers acting as a single coherent beam, focusing on a sail just meters across, maintaining that focus as the spacecraft accelerates away at tremendous speed. Any misalignment destroys the probe. Any fluctuation in power burns through the sail. The precision required exceeds anything humanity has built at comparable scale. Even if you solve those problems, you face the interstellar medium. Space isn't empty. It contains dust particles, hydrogen atoms, tiny grains of matter. At 20% light speed, colliding with a dust grain releases energy equivalent to an exploding hand grenade. A spacecraft traveling at those velocities needs shielding that can survive continuous impacts. But shielding adds mass. Added mass requires more energy to accelerate. More energy means bigger lasers and more infrastructure. The requirements spiral upward. Assume you solve everything. You launch a successful probe. It reaches Alpha Centauri 20 years later. It begins transmitting data. Now you face the communication challenge. The probe weighs grams. It has minimal power for transmission. Its signal spreads across 4 light-years of distance. By the time that signal reaches Earth, it's almost indistinguishable from background noise. You need enormous receiving arrays, sophisticated signal processing, years of observation time to extract meaningful data from the faint whisper crossing interstellar space. Every technical challenge has theoretical solutions: better materials, more powerful lasers, improved electronics, clever engineering. But theoretical solutions require practical implementation. They require funding, political will, sustained effort across decades, international cooperation. None of those things are guaranteed. Most ambitious space projects fail not from technical inadequacy, but from withdrawn funding or lost political support. The International Space Station represents humanity's most expensive single object ever built. Roughly $150 billion invested over decades, multiple nations contributing. It orbits 400 kilometers above Earth. Alpha Centauri sits 40 trillion kilometers away. That's a factor of 100 billion times farther. Even accounting for technological progress and economies of scale, the cost differential remains staggering. Maybe that's acceptable. Maybe humanity should invest enormous resources in reaching Alpha Centauri, even if success remains uncertain. Maybe the attempt itself justifies the cost. Maybe pushing against impossible limits advances science and technology in unexpected ways. Apollo didn't just land people on the moon. It drove innovation in materials, science, computer technology, systems engineering. Maybe an Alpha Centauri mission would do the same at larger scale. Or maybe that investment would be better spent elsewhere. Better telescopes to observe Alpha Centauri from Earth. Better instruments to detect its planet's atmospheres. Better models to simulate potential habitability. You can learn enormous amounts about distant star systems without sending physical probes. The James Webb Space Telescope revealed unprecedented detail about exoplanet atmospheres from Earth orbit. Future telescopes will see more. Direct observation might provide better science per dollar than interstellar missions. This creates philosophical tension. Do we explore because exploration yields practical benefits? Or because exploration represents something fundamental about human nature? Are we trying to solve scientific problems or satisfy psychological needs? The answer determines how we approach Alpha Centauri. If it's about science, stay home and build bigger telescopes. If it's about human identity and destiny, launch the probes regardless of cost. Both perspectives have merit. Both reflect genuine human values, but they suggest different futures. One future finds humanity building increasingly sophisticated instruments to observe the cosmos from our solar system, becoming expert astronomers, masters of remote sensing, understanding the universe through careful observation from a distance. The other future sees humanity struggling to build interstellar probes, launching tiny craft into the void, waiting decades for responses, gradually extending our physical presence beyond the solar system, even if that process takes centuries or millennia. Neither future is wrong, neither is right. They're just different paths forward, different responses to the same basic reality that Alpha Centauri sits very far away. That distance doesn't care about human preferences. It doesn't accommodate our desires. It simply exists. Physics doesn't negotiate. Some might find that depressing. The universe's indifference to human ambition. the cold mathematics of distance and energy, the barriers that technology can't easily overcome. But there's also something clarifying about hard limits. They force honesty. They prevent wishful thinking. They make you confront reality as it actually exists rather than as you wish it existed. Alpha Centauri teaches humility through sheer existence. Not the false humility of pretending humans are insignificant. We're not. We're remarkable. We built civilization. We developed science. We explored our own planet thoroughly and began exploring nearby space. That's genuinely impressive for a species that only developed agriculture 10,000 years ago. But impressive doesn't mean unlimited. Capability doesn't mean omnipotence. We can do extraordinary things within our domain. We struggle beyond it. That limitation might be universal. Other civilizations around other stars probably face similar constraints. They probably developed radio telescopes and detected hints of planets orbiting distant suns. They probably calculated the distances and energy requirements. They probably reached similar conclusions about the practical impossibility of casual interstellar travel. They're probably trapped in their home systems, just as we're trapped in ours. All of us able to observe, unable to visit. The galaxy might contain thousands of intelligent species, all isolated by distance, all staring at unreachable neighbors. If that's true, it changes how we should think about the search for extraterrestrial intelligence. We're not looking for visiting aliens. We're looking for radio signals from distant civilizations who face the same isolation we face, who developed similar technology, who made similar discoveries, who reached similar limitations. The search becomes about finding others in the same situation, rather than expecting visitors who somehow overcame barriers we can't overcome. Maybe that's the real lesson of Alpha Centauri. Not that humans are insignificant, that the universe is big, profoundly big, big enough that distance itself becomes an isolating factor, big enough that proximity is relative, big enough that nearest neighbor still means impossibly far. We live in a universe where you can see other destinations clearly, but cannot reach them practically, where knowledge exceeds capability, where understanding outpaces action. That's not a comfortable realization. Humans prefer problems they can solve through effort and ingenuity. We like challenges that yield to persistence. Alpha Centauri doesn't yield. It sits there, visible, known, characterized, unreachable. A permanent reminder of limitation, not a temporary obstacle awaiting the right technology. A fundamental barrier built into the architecture of space and time. You can measure the distance precisely. You can calculate trajectories accurately. You can design theoretical missions completely. You cannot travel there within relevant human timescales using known physics. That's not pessimism. That's accuracy. The math doesn't lie. The physics doesn't care. Alpha Centauri remains exactly where it is, regardless of human wishes. Future generations might develop technologies we can't currently imagine, physics we don't yet understand, methods that bypass current limitations. That's possible. History shows technology advancing in unexpected directions. But betting on unknown future breakthroughs means admitting current approaches are inadequate. It means accepting we can't reach Alpha Centauri now. Maybe not for centuries. Maybe not ever. Some will continue trying anyway. Some will dedicate careers to developing better propulsion, to solving the energy problems, to designing workable interstellar probes. That work has value even if it never succeeds. even if Alpha Centauri remains forever beyond reach. The attempt teaches us about engineering limits, physical constraints, the nature of space itself. Others will focus on observation rather than travel, on understanding Alpha Centauri from a distance, on characterizing its planets remotely, on determining whether life exists there without ever visiting. That approach also has value, also advances knowledge, also satisfies curiosity about our nearest stellar neighbor. Both approaches accept the same underlying reality. Alpha Centauri is far, terrifyingly far, so far that human intuition fails to grasp the distance, so far that conventional travel becomes meaningless, so far that even revolutionary propulsion barely makes a dent in journey time. The distance doesn't shrink because we want it to. It remains fixed, absolute, uncaring. That's what makes it terrifying. Not that it's dangerous, that it's indifferent. The universe doesn't notice human ambition, doesn't accommodate our dreams, doesn't care whether we explore or stay home. Alpha Centauri will continue orbiting the galaxy, whether we visit or not. Its planets will continue their endless circuits regardless of human interest. The stars will burn, the distances will remain, and Earth will keep circling its own star, separated from its nearest neighbors by gulfs that might as well be infinite for all practical purposes. 25 trillion miles, 4.37 light-years, 277,000 astronomical units. The numbers describe the same reality from different angles. Alpha Centauri sits close enough to see clearly, far enough to remain permanently out of reach, with any technology that respects the laws of physics as we currently understand them. That's the truth of interstellar distance. Not exciting, not inspiring, just true. The closest star system to our own might as well exist in another universe for all the access we have to it. We can observe, we can measure, we can calculate, we can dream. We cannot visit. Not now. Probably not for centuries, if ever. That realization forces us to confront something fundamental about our place in the cosmos. We're conscious beings trapped by distance on a small planet orbiting an ordinary star. We can see the universe. We cannot easily explore it beyond our immediate neighborhood. The galaxy spreads out around us, visible but inaccessible, knowable but unreachable. Alpha Centauri teaches this lesson with brutal clarity every time we look at its light in the night sky, close enough to tantalize, far enough to humble. The terrifying distance to our nearest stellar neighbor isn't a problem waiting to be solved. It's a fundamental feature of the universe we inhabit,